Dear students, it's very much interesting to communicate with you all through this video lectures. In this, we will discuss about the CPU scheduling concepts and what is the importance of the scheduling concepts and the algorithms that we are using in the CPU scheduling in this video. The CPU scheduling algorithms helps the operating system to work successively. Here, the scheduling. It allows one process to use the CPU while the execution of another process is in hold. And the process may be in a waiting state and due to the unavailability of the resource. So that if the process in a waiting state means the CPU have to decide which process the processor have to be given. Actually, the aim of the CPU scheduling is to make the system efficient, fast, and fair. There are two types of scheduling. One is preemptive scheduling, and the next one is non-preemptive scheduling. In preemptive scheduling, it allows the running process to be interrupted by the high priority process, which means if one process is running, the another process which has the higher priority can interrupt the currently running process. And in non-preemptive scheduling, the new process, even though it has a higher priority or the lower priority, the newly coming process has to wait until the currently running process finishes its CPU cycle. Then the benefit of using the CPU scheduling. Here we have increased efficiency while using the CPU scheduling in operating system, because increased efficiency, it maximizes the CPU usage so that it increases the efficiency and it reduces the idle time. Actually, allocating the CPU to the resource in a circular basis or in the queue basis means there is no need of idling the CPU. Next one is the improved resource utilization. The processor is allocated from one process to the another process in a sequential basis so that the resources will also be used effectively, so that there is increased efficiency and there is no idle time and there is an improved resource utilization. Here, there are 5 algorithms that we can use with this CPU scheduling algorithm. First one is first come, first served scheduling. Second one is shortest job first scheduling. Next one is priority scheduling. And the fourth one is round robin scheduling. And the fifth one is multi-level queue scheduling. In first come, first served scheduling, it allocates in this FCFS policy, the CPU is allocated to the process to which process it requests the first. That means the first to come, first to serve. The first to come process can be served first. And the next process which arrives in the queue can get the CPU next. Here, in this example, we can understand about the FCFS policy. There are 3 processes, P1, P2, P3, and its burst time. Burst time is otherwise called as the CPU execution time. That means the process takes some time for executing its process. It's called as the burst time. Here, the P1 process requires 24 milliseconds and P2 process requires 3 milliseconds and P3 process requires 3 milliseconds. Here, these 3 processes work in a sequential manner. Then we will see how the processor is allocated through these processes And this work is depicted in a bar chart, otherwise called as a Gantt chart. You'll see here. Here you will see three processes arrive at 0th millisecond, and P1 arrives first so that it gets the CPU first. From 0th millisecond up to 24th millisecond, the P1 is using the processor. At the end of the P1 process execution, P2 gets the processor. From 24th millisecond up to 27th, the P2 process will have the CPU for its execution. And from 27th to 30th, the P3 process will get the processor for its execution. Here, for completing, here in the previous example, we'll see that P2 and P3 requires only 3 milliseconds for their execution. Here, for the executing this 3 milliseconds, P2 and P3 have to wait up to 24 milliseconds, because here the FCFS scheduling algorithm uses the policy of which process arrives the first will get the processor immediately. So that the second process, even though it has a low executional time, but it had to wait up to the first process finish its processing. Here, the waiting time is 0 millisecond for process P1 because it arrives the most, first most. And the 24th millisecond, the process P2 arrives, and the 27th millisecond, and the process P3 gets the processor for execution. So that the average waiting time is calculated as 0 plus 24 plus 27 divided by 3, because 3 processes. So that we have dividing these average waiting time with 3, and we get 17 millisecond as the average waiting time. If we shuffle these process, because they are based on the FCFS policy, the first come process will get the CPU. Here, if process P2 arrives first, P3 next, and P1 last, means what will the Gantt chart shows? At the 0th second, P2 receives the CPU for its execution. Up to 3 millisecond, it holds the CPU. After a 3rd millisecond, P3 arrives, and up to 6th millisecond, P3 is having the processor for its execution. At the 6th millisecond, P1 gets the processor for execution up to 30th millisecond. Here, the average waiting time is now 6 plus 0 plus 3 divided by 3 is equal to 3 millisecond. Here, if based on the previous example and this example, the average waiting time is quite different. So that what we understood is depends upon the process arrives, the waiting time will be different. That means the CPU burst time will vary. Next one is shortest job first scheduling. In this algorithm, the CPU will be assigned to the process with the shortest next CPU burst. For example, it aims in this shortest job first scheduling. The main aim of this is to minimize the average waiting time for all the incoming process, so that we have to prioritize the shortest job first for allocating the CPU. In this, we'll see one example. In this same length, for example, in this third point, we will see that if 2 or more processes have the same length, for this, in the previous example, we see now P2 process P2 and P3 have equal 3 milliseconds for their execution. So that if the equal burst time is required for 2 or more processes, means we will use the FCFS policy. Otherwise, in this method, we will use the shortest job first scheduling policy in this example. Here, we'll see process P1, P2, P3, P4, and its burst time is 6, 8, 7, and 3. Through these shortest job first scheduling algorithm. Here we have to allocate the shortest job first to the CPU. Based on this, the P4 gets the CPU for execution. So that P4 is assigned first. You can see in this Gantt chart. And at the end of the third millisecond, P1 will receive the CPU for execution. At the 9th millisecond, P3 will get the CPU for its execution because it has 7 milliseconds for its execution. At last, P2 requires the CPU for execution up to 8 milliseconds. The waiting time is 3 milliseconds for process P1 and 16 milliseconds for process P2 and 9 milliseconds for process P3 and 0 millisecond for process P4. Here, the average waiting time is 3 plus 16 plus 9 plus 0 divided by 4 is equal to 7. Here, 4 means 4 processes are there. So that for getting the average waiting time, we have to divide it with 4. And here, the average waiting time is 7 milliseconds. By comparison, the FCFS policy with the SJF, shortest job first algorithm, the waiting time, average waiting time is less compared to the FCFS policy. Here, the SJF algorithm can be either preemptive or non-preemptive. Preemptive means interrupted by the higher priority process, and a non-preemptive means though it is though the incoming process may be a high priority or low priority, it has to wait until the completion of the currently running process. And the third one is the priority scheduling. Priority scheduling may be defined internally or externally. Here, in this priority scheduling, priorities may be defined internally or externally. Internally means the priorities are set based on some measurable quantities like the time limits, memory requirements, number of open files, and the ratio of average input-output burst to the average CPU burst process. And based on this external priorities, the priority is set outside the OS based on the importance of the process, the type and amount of funds being paid for that process, the department sponsoring for that work, political factors, etc. are considered outside the OS as an external priority. And while comparing this with the previous two FCFS and SJF, here the priority scheduling can be either preemptive or non-preemptive. And based on this priority scheduling, when a process arrives at a ready queue, its priority is compared with the priority of the currently running process. And if the running process has the low priority, means the incoming process will get the CPU. Otherwise, it will remain idle up to the currently running process. In this priority scheduling, the major problem is indefinite blocking or starvation. Indefinite blocking or starvation means the new process have to wait based on its priority. And here, the starvation or indefinite blocking is solved by a process called aging. Aging means you can gradually increase the priority of the process, depends upon its waiting time. If it waits for a long time, means you can increase the priority by every 1 to 15 minutes. So that it's like an age, the priority will also increases every 15 minutes. So that the processes will go to the topmost to get the attention of the CPU. Next one is the round robin scheduling. In this round robin scheduling, this algorithm is working based on the time sharing process. While comparing to this FCFS scheduling, here round robin scheduling is based on preemptive concept. Here, why we are saying that is, it may be interrupted. Here, this algorithm uses the time sharing means it uses a time quantum or a time slice such as 10 to milliseconds length for allocating the CPU to the process. To implement this round robin scheduling, the process should be kept in a ready queue That ready queue works in a circular order in the first come, first served. That is first in, first out operational concept. So new processes are added to the tail of the circular queue. Every new process will add at the end of that circular queue. That means the tail of the circular queue. If the CPU scheduler picks the first process from the ready queue, means the timer will starts, and while the timer reaches its time quantum, it dispatches the process, and the next process will get the attention from the CPU. Here, the process itself will release the CPU voluntarily, after the completion of the time slice, so that in this example we will understand how this round robin will work. In this Gantt chart, you will see here there are three processes, P1, P2, P3. P1 requires 24 milliseconds, and P2 requires 3 milliseconds, and P3 requires 3 milliseconds. In this, here, for time quantum is used. For time quantum is followed here in this round robin scheduling. P1 complete dispatches or voluntarily release the CPU, and while attaining the 4th millisecond, and releases the CPU and transfer it to the P2. And now P2 requires only 3 milliseconds. Actually, the time quantum is allocated as 4 milliseconds, but P2 voluntarily dispatches or releases the CPU at the 7th millisecond after completing its execution. And P3 now gets the CPU for its execution at the 10th millisecond, because here also 4 milliseconds are allotted as a time quantum or a time slice, but P3 requires only 3 milliseconds for execution. So at the 10th millisecond, it voluntarily releases the CPU, and now the P1, because here the processes are kept in a circular queue, so that now the processor or the CPU will transfer to P1 at the 10th millisecond. At P1 also releases. Actually, P1 requires 24 milliseconds, but based on the time quantum, it releases the CPU at the 14th millisecond. Now again, it transfers the CPU to, again, the CPU remains with the P1. Now up to the 18th millisecond, because the 4 time quantum is followed here. And again, 18 plus 4, 22. Now P1 is now having the CPU with its for its execution, and ends its work at the 4th millisecond, so that 18 plus 4 is 22, and now 22 plus 4, 26. Now P1 is also P1 is having that processor with its CPU with its now, and now at the 26th millisecond, it completes and voluntarily releases the CPU, and again it uses the CPU at the 26th millisecond, and now the timer shows at the end of the 30th millisecond, it completes its process. Here, the average millisecond is calculates as 10 minus 4. That means the 6 milliseconds for P1, and P2 4 millisecond, and P3 7 millisecond. Thus, the average waiting time is 17 divided by 3, and now it is 5.66 millisecond. This RR scheduling algorithm works in the preemptive process, preemptive scheduling basis. That means it may be interrupted based on the time interrupt. And the next one is the multi-level queue scheduling. Here, there are the processes in this scheduling algorithm. The incoming processes are grouped in classified with 2 groups. One is a foreground process, that is also called as interactive process. And the next one is a background process called as the batch process. These foreground process and background process have different response time and different scheduling needs also. Here, the incoming processes are divided as system process, interactive editing process, batch process, and student process. Based on this process, priorities, highest priority or lowest priority may be set to this incoming process, every process. Here, a separate queue will be followed for both the foreground and the background process, and each process has its own scheduling algorithm. For example, if the foreground queue or the foreground groups followed RR algorithm, that means a round robin algorithm, means the background queue may use an FCFS algorithm. There is no need of both have to use the same type of algorithm here. Next one is the multi-level feedback queue scheduling. In this variation of multi-level, this algorithm is an additional one based on this multi-level queue scheduling. It is also called as a multi-level feedback queue scheduling. It is a variation of multi-level queue scheduling. In this, the processes can move between queues. Here, processes will move between the queues based on their behavior and needs. In this queue, the process can move from front to back based on its needs. This this moving adaptability allows the system to favor for short processes while preventing starvation of longer processes. In this, based on this multi-level feedback queue scheduling, the process have to move front and back in the queue so that the shortest jobs will get the more attention, so that here the starvation is prevented, so that there is no need of shortest job have to wait for longer time. This process starts in the higher priority queue. The execution starts from the highest priority queues. If a process does not complete within its allotted time quantum, means the CPU will be transferred to the lower priority queue. The process that waited too long in lower priority queues may be promoted back to the high priority queues for that preventing starvation here, so that the jobs or the processes can move in between the queues from front to back, so that it gets the lower and the higher priorities. While discussing all these algorithms, and we'll have a tabulation here, based on this tabulation, we'll see how can these algorithms helpful for us for working in OS. These based on this, FCFS is preemptive, or based on this heading, preemptive, fairness, average waiting time, complexity, and best use cases. We'll allocate these algorithms and classified this based on the features of that algorithm. And based on this, the multi-level feedback queue has the highest complexity, so that the dynamic and diverse process loads will be done here. And while using the FCFS policy, simple batch systems can be used. And here there is waiting time is high, but the complexity is low. And while comparing to these algorithms, the round robin and multi-level queue has the lowest average waiting time and high fairness too while using this algorithms. And as a conclusion, we'll see basically the scheduling algorithms are developed to optimize the CPU utilization and minimize the waiting time and turnaround times and ensure fairness among the processes. While each algorithm has its strength and weaknesses, the choice of scheduling algorithm depends on the specific needs of the system, because here you'll see that based on the needs and the requirements of the process, we may use any algorithm based on the requirement. Students, I think you will get understood about the topic of this scheduling algorithm, which is an important topic in the operating system. And it's very much interesting, and without disturbances, to communicate and convey whatever the idea we will have about that topic with you all through this video. Thank you.